this section, we're going to be looking at some of the basic trig identities. And then in the next section, we'll look at some non-basic identities, a little bit more complicated ones. And then after that, we'll talk a lot about solving identities, proving identities. All right, well, the basic identities, a bunch of them we already know. For example, we know sine x is 1 over cosecant x, which can also be written as cosecant x is 1 over sine x. And we have the same thing for cosine and secant. Secant x is 1 over cosine x. And tangent and cotangent. Tangent x is 1 over cotangent x. And cotangent x is 1 over tangent x. And we also have tangent x is sine x over cosine x. And cotangent x is cosine x over sine x. All of those we saw show up in previous material. Here's a couple that I'm not sure we've looked at before. Sine of x, sine of minus x, is minus sine of x. And tangent of minus x is also minus tangent of x. But cosine of minus x is cosine of x. All right, so let's talk about those for a minute and see why these make sense. Let's say I had this angle is pi over 6. We go to that table that we've memorized. We know that sine of pi over 6 is a half, and cosine of pi over 6 is square root of 3 over 2. Now, what happens if I take this angle, which is negative pi over 6? Then notice what happens. Sine of negative pi over 6, negative pi over 6, that's in quadrant 4. In quadrant 4, sine is negative, so I get negative 1/2. On the other hand, cosine of negative pi over 6, negative pi over 6 is in quadrant 4. In quadrant 4, cosine is positive. So that gives you an idea of why, when you have sine and you have a negative sign inside your brackets, then minus sign comes out front, where when you have cosine and you have a minus sign inside your parentheses, you don't get a minus sign out front. And you can check, the same thing works for tangent. Okay? There's actually some names for these, and the names are, we would say sine and cosine are odd functions, while sine and tangent are odd functions, while cosine is an even function. And I think we talked about even and odd functions back a long time ago in this course, but we talked about even and odd in terms of polynomials. All right, the next group of identities you should know, there's really one of them, but we write it in a whole bunch of different forms. It's called the Pythagorean identity. Called the Pythagorean identity for a good reason. Looks a lot like the Pythagorean theorem. And here's the way that one works. Let's say we have a triangle, a right triangle. You don't have to do this using a right triangle. You can also do it with the unit circle definition, and it works out. And we've got our angle. We're using x for angles in this chapter, I guess, for some reason. And then I'll call this opposite. This is adjacent, and this is hypotenuse. All right, well, what happens when I take sine squared x plus cosine squared x? Sine squared x plus cosine squared. Well, sine is opposite over hypotenuse. That's going to be opposite over hypotenuse squared. Cosine is adjacent over hypotenuse. That's adjacent over hypotenuse squared. So we end up with opposite squared plus adjacent squared over hypotenuse squared, right? Because they both have hypotenuse squared on bottom, so I can add the tops. But now, go back to your Pythagorean identity, your Pythagorean theorem, I mean. A squared plus b squared is c squared. That's the same as saying opposite squared plus adjacent squared is hypotenuse squared. So this becomes hypotenuse squared over hypotenuse squared, which is 1. So there's the first of the Pythagorean identities. Sine squared x plus cosine squared x equals 1. And then you'll see it written in alternative forms. You'll see sine squared x is 1 minus cosine squared x, and cosine squared x is 1 minus sine squared x. So there's the first three forms of the Pythagorean identity. And since I say first three forms, it makes you probably guess that, yeah, there's more forms. Here they are. Let's say I had sine squared x plus cosine squared x equals 1, and I chose to take this equation and divide everything by cosine squared x. Then look what I end up with. Sine squared over cosine squared, that's tangent squared x. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared x. So there's another version of the Pythagorean identity. Tangent squared plus 1 equals secant squared. And you'll see this one written in other ways. You'll see it as tangent squared x is secant squared x minus 1. Or sometimes you'll see it written as secant squared x minus tangent squared x equals 1. Okay, almost done. We got three more of them. Let's say I were to take sine squared x plus cosine squared x equals 1, and this time I choose to divide everything by sine squared x. Then I would have 1 plus cotangent squared x equals cosecant squared x. And again, this is written in alternative forms. You'll see 1 equals cotangent squared, 1 equals cosecant squared x minus cotangent squared x. And the last common form you see this written in, you'll see cotangent squared x equals cosecant squared x minus 1. So there's a whole list of the Pythagorean identities. There's really one of them. Sine squared plus cosine squared equals 1. All the others are alternative forms of writing the same identity. All right, so I'm going to grab some problems out of the book here, and then we have one more group of identities to look at. We'll take a look at those. All right, so the first group of problems I see, they're going to ask you to simplify stuff. So you might have something like sine x plus cosine x times secant x plus cosecant x. Okay, well, the fact that you have sines and cosines and secants and cosecants isn't any big deal, really. You do FOIL just like you always do. So you're going to have sine x times secant x plus sine x times cosecant x plus cosine x secant x plus cosine x cosecant x. But then you go ahead and you simplify. And what I mean by simplify is you can write this as sine x times 1 over cosine x plus this one becomes sine x times 1 over sine x. That's a fancy way of writing the number 1. Same thing with this one. This is cosine x times 1 over cosine x. That's also 1. And this one is cosine x times 1 over sine x. All right, so let's look at what we have here. We have sine x over cosine x. That's tangent x. Then this one is the number 1. This one is the number 1. 1 plus 1 is 2. And this one is cosine over sine. Cosine over sine is cotangent. So we FOIL it out. We use our identities. Simplify it. There's what we get. Okay, how about one more of these maybe? About sine x minus cosine x, whole thing squared. All right, well, you might do this. You might write this as sine x minus cosine x times sine x minus cosine x. FOIL it out. I get sine squared x minus sine x cosine x minus sine x cosine x. Now notice I switched the order on that one. It was cosine sine. I have to switch the order. Plus cosine squared. All right, but then what I see is I have a sine squared plus a cosine squared. Sine squared plus cosine squared is 1, and then I've got two of the same things. So that's minus 2 sine x cosine x. So there's how you use that Pythagorean identity. Sine squared plus cosine squared equals 1. All right, the next group I see in your book, they ask you to factor. I'll do one of these. Factor, the directions might be 2 cosine squared x plus cosine x minus 3. This technique of factoring will become important when we go to solve equations. This really isn't anything new. Think of this as just being 2y squared plus y minus 3. I'm sure if I gave you 2y squared plus y minus 3, you could factor it. The fact that you have cosine squareds and cosines in there really isn't any different. Cosine x, think of that as one variable. Cosine squared x, that's a variable. So what are you going to have? You're going to have parentheses that look like this. You're going to have a 2 cosine x and a cosine x to get the 2 cosine squared in front. And then you've got to have a 3 and a 1. Let's try the 3 there and the 1 there. And then I think I have to have a plus 3 and a minus 1 like that to get the plus cosine x in the middle and the minus 3 on the end. So just FOIL it out, check, convince yourself that it works. All right, the next group we're going to have, again, we're back to simplify. And they're going to give you some things that are fractions, I guess. So I see, oh, here's a good one, I guess. Sine to the 4th x minus cosine to the 4th x over sine squared x minus cosine squared x. And what you have to do on these, in order to simplify, when you have a fraction, you always need to factor. Factor and reduce. I can't just cancel out the sine to the 4th and the sine squared there. That's a very common mistake. I can't cancel this out because they're connected by minus signs. All right, so I factor. And what I notice is, again, it kind of goes back to this. If I have a to the 4th minus b to the 4th, I think of that as being a squared squared minus b squared squared. So that factors as difference of squares, a squared minus b squared, a squared plus b squared. So that's really what I'm looking at on top. My sine to the 4th, I think of that as sine squared squared. Cosine to the 4th, that's cosine squared squared. So anyway, this factors as sine squared x minus cosine squared x times sine squared x plus cosine squared x divided by sine squared x minus cosine squared x. Now I can reduce. Now I've got a factor of sine squared minus cosine squared on top and a factor of that on bottom, so I reduce those. Oh, but then I notice something nice. Sine squared plus cosine squared, that's the number 1. Okay, so you're going to have some problems that look like that, where you have to factor, reduce, cancel your fractions out. All right, the last thing I see in this section are what are called the sum and difference identities. Sum and difference identities. I'm not going to go through the proof of these. The proof of these is given in your book. You can look it up. But it turns out that these are very important identities. These identities will really be the key to all of the other identities that we have in the next section. And they look like this. The sine of u plus v is sine u cosine v plus sine v cosine u. The sine of u minus v is the same formula, except you got a minus sign in the middle. Sine u cosine v minus sine v cosine u. And then there's ones for the cosine. Cosine of u plus v is cosine u cosine v minus sine u sine v. All right, so notice the difference here. Difference, bad joke when I'm talking about subtraction. But what I meant was, in the sine of u plus v formula, notice in the sine of u plus v formula, you've got a plus in the middle. But in the cosine of u plus v formula, you actually have a minus in the middle. And it switches to, when you do the cosine of u minus v formula, you get cosine u, cosine v, plus sine u, sine v. So notice there's a sign switching thing. And that really comes back to that fact that sine of negative x is negative sine x. If you look at the proof, that's really where that comes from. All right, finally, there's some formulas for tangent. Tangent of u plus v is tangent u plus tangent v divided by 1 minus tangent u, tangent v. So that one's got a combination of the two things. It's got a plus here on the left-hand side. It's got a plus and a minus on the right-hand side. And as you would suspect, if I flip it, if I write tangent of u minus v, the signs change. This becomes tangent u minus tangent v over 1 plus tangent u, tangent v. All right, so the first thing I want to convince you of is that what you think should work with sine and cosine, or what your first guess might be, simply doesn't work. For example, what I mean is, what if I asked you to take the sine of 30 degrees plus 45 degrees? You would be very tempted to say that's sine of 30 degrees plus sine of 45 degrees. Unfortunately, that's very wrong. And the easiest way to tell is we'll look at decimal expansions here. This is sine of 75 degrees. Over here, this is, well, sine of 30, we know that one, that's a half. And the sine of 45, that's square root of 2 over 2. That doesn't help a whole lot. So I got to switch my calculator to degrees mode here. And then I'm going to do sine of 75. Sine of 75, my calculator tells me this is 0.9659 roughly, where sine of 30 plus sine of 45, that's 1.207. All right, so unfortunately, sine and cosine don't work that way. Not terribly surprising, because truthfully, almost nothing works that way. For as a very simple example, if I have a plus b squared, that's not the same as a squared plus b squared. If I have a plus b squared, I have to FOIL it out, and I get a squared plus 2ab plus b squared. So that property of being able to split on the plus sign there, that's really called linearity. And it's not surprising that linearity doesn't work for sine, cosine, because they're not linear. When we draw the graph, you'll see they're really not linear. And the same with this a plus b quantity squared. That's a quadratic thing. It's not linear. Okay, so what is the sine of 75 degrees? Well, we get that decimal, but we could also do this. The sine of 75 degrees is the sine of 30 degrees plus 45 degrees. And then we can use that formula. According to the formula, that's sine 30 degrees cosine 45 degrees plus sine 45 degrees cosine 30 degrees. Sine of 30 degrees is a half. Cosine of 45, square root of 2 over 2, plus sine of 45, square root of 2 over 2, cosine of 30, square root of 3 over 2. So I have square root of 2 plus square root of 6 all over 4. Now let's check that into our calculator and see if we get this 0.9659 number still. So square root of 2 plus square root of 6. I got 3.86, and I got to divide that by 2. I get, I had to divide it by 4, not divide it by 2. Had the wrong answer there. I was confused. Divide by 4. Divide by 4, I do get the 0.9659, so it does seem to work. All right, so one more of these problems. How about if I gave you the cosine of pi over 12? Well, when we're working in degrees, it's pretty easy. It was pretty easy for you to see that 75 degrees is 30 degrees plus 45 degrees. But what about pi over 12? Well, what you got to do, the angles we know in radians are pi over 3, pi over 4, pi over 6. So we need to figure out a way to write pi over 12 using pi over 3, pi over 4, pi over 6. All right? It seems to me as though I probably want to use pi over 3 and pi over 4 because those would have a common denominator of 12. So let's see, pi over 3 is bigger than pi over 4 because the bottom's bigger. So I'm hoping that maybe pi over 3 minus pi over 4 will give me pi over 12. Let's see. That would be 4 pi over 12 minus 3 pi over 12. That does work. All right, so that can be a little bit challenging with these. Working in radians is finding the combination that you need to work with. So this becomes cosine of pi over 3 minus pi over 4. So I look up to that cosine formula. That's cosine pi over 3, cosine pi over 4, plus sine pi over 3, sine pi over 4. So cosine of pi over 3. Do you remember cosine of pi over 3? Half. Cosine of pi over 4, square root of 2 over 2. Plus sine of pi over 3, that's square root of 3 over 2. Sine of pi over 4, that's square root of 2 over 2. So for my answer, I get square root of 2 plus square root of 6 over 4. Curious. That's exactly the same answer I got for sine of 75 degrees. Why is that? Well, for a couple of reasons. Your answers are pretty much always going to have these square root of 2's, square root of 6's in them. Why? Because we're always using the same angles. We're using 30 degrees, 45 degrees, and 60 degrees. And so we're going to end up with the square root of 2 over 2's from the 45 degrees and the square root of 3 over 2's from the 30 and the 60, depending on if you're dealing with sine and cosine. So your answers on these problems are always going to be really pretty similar. It's just a matter of where you have pluses in between or minuses in between. Just so happens I picked two examples where you get exactly the same answers. A little bit of a coincidence there, but the answers are going to be very similar on these.